Okay, so this video is going to be the last of chapter 8. The first thing that we're going to talk about is resonance structures. I don't want you to overthink when we're talking about resonance structures. They're pretty straightforward. They happen all throughout nature. So let's kind of dive into this. So when we think of electrons, we need to think of them as a fluid thing, right? When we draw a Lewis structure, we're drawing them in two dimensionals, right? In two dimensions, right? So when we think of them, though, we have to realize that they're not two-dimensional things, they're three-dimensional things. So a resonance structure is when there are multiple placements for the atoms or the electrons in a molecule. So let's look at the example of ozone here. So ozone is drawn like this. Its ozone is actually O3, okay? So this is one way you can draw ozone. You can draw ozone with the single bond here on the left-hand or on the right-hand side, and then over here you can draw ozone over here on the left-hand side. And you'll notice that there's this little arrow here. This arrow is indicating that there is a resonance here, which means that you can draw the Lewis structure of these two of ozone in either way, okay? Now, in nature, it's not like you're walking around and you happen upon an ozone that has the single bond on this side, or you happen upon a Lewis structure of ozone that has the single bond on that side. That's not how it works, okay? Those electrons that are in the ozone are moving from one to the other constantly. It's almost like a delocalization of some sort. So let's kind of think about it as the primary colors, right? So your colors show up a little bit better on your slides, but we can kind of talk through this. So let's think of this ozone with the single bond on the right-hand side as blue, and the ozone with the single bond on the left-hand side is yellow. We know when we mix blue and yellow, we get green, okay? So ultimately, it's sort of the same thing here. When I mix these two resonance structures together, I'm sort of getting a one molecule where it's not that the electrons are switching from one to another. It's just sort of like they're living in this coharmonious thing where it just happens to have green in one area. So when you draw Lewis structures, if you have a single bond that's somewhere that could also be drawn somewhere else, you are responsible for knowing that you have to draw those two or three or possibly four. There's lots of times you can have multiple resonance. You are responsible for drawing all of the types or all of the possible resonance structures and then indicating that they're resonance by using an equilibrium arrow. Okay, so that's resonance structure. Okay, which I have double here. Okay, let's talk about the exceptions to the octet that we can have. There are 3 exceptions to the octet, and the 3 that we come across tend to be the same every single time. So the first one is you can have an odd number, so the molecule NO. Nitrogen has 5 valence electrons, oxygen has 6, so we end up with 11 valence electrons. So I can draw this Lewis structure like this. That's one way. And then it can have resonance where oxygen has the lone pair. So nitrogen has the double, 2 doubles, and oxygen's the one that has the single. Okay, so that's another example of a resonance. So that's one exception to the octet. You can also have a compound that contains fewer electrons than 8. An example of this one is BF3. So boron tends to be okay with just having 6 electrons instead of the 8. And that's because if you'll realize it's sort of in that same row, it's in that 3A, just like aluminum. So it tends to be okay just having 6 electrons. And then obviously if you can have a compound that has fewer electrons than 8, you can also have a compound that contains more electrons than 8. And an example of that is xenon hexafluoride. So that will look something like this. It'll have fluorine. It'll have 6 fluorines, and I'm not going to draw all of fluorine's electrons. You can do that like this. I'm not going to go around. So this is, we call this an expanded octet, meaning that it goes past the octet. You'll also see sometimes halogens will tend to be okay with having expanded octets as well. And then the last thing from chapter 8 is relative strengths and lengths of covalent bonds. Okay, so we know that we have single, double, and triple bonds. Let's talk about their strengths and their lengths. So one would think that the highest strength for a bond is going to be triple, and that is correct because it's sharing 6 electrons. So it's going to have the highest bond enthalpy, which means it's going to have the strongest between those 6 electrons, which also then means if it's sharing 6 electrons, the space between the atoms is going to be minimalized. So not only does the triple bond have the highest bond enthalpy, it's also going to be the shortest bond length. And then the single is going to have the lowest bond enthalpy and the longest length. And then obviously the double is just going to be somewhere in the middle. Okay, so think about it like this. Think about single bonds, you and somebody just sort of shaking hands. Okay, think about a double bond as sort of like, you're holding both of your hands, and then a triple bond would be like a hug with like a leg wrapped around them. Like you really want that person really close to you. Okay. All right, and then we can also calculate the delta H for a reaction based off of the bond enthalpies, which is something that we've already done, but let's look at another example of this. So it says, use the table above, estimate the delta H for the following reaction. So let's review our equation here, which is also on your equation sheet that you are provided. So the enthalpy of a reaction is equal to the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants. Okay, so if I look here, I'm going to see what's going on here. So I have a carbon double bond carbon here, and then I notice that it's a single down here. So these hydrogens aren't actually leaving the carbon. So really the only thing that I'm breaking is this carbon double bond. And then over here, same thing, this oxygen and hydrogen, those aren't leaving. So really the only thing here that I'm breaking is this oxygen-oxygen bond. So I'm going to go up here. So carbon breaking is 614 kilojoules per mole. And I'm going to add my oxygen-oxygen single bond, which is 146 kilojoules per mole. And I get, if I can find my calculator, the sum of those 614 plus 146, that comes out to be 760 kilojoules per mole. Okay, and then I'm going to subtract whatever is being formed. Okay, because you have to remember, in order to break a bond, you have to put energy into it. So that's why this is positive. So the reason why we're subtracting the reactants is because when we create bonds, we are actually releasing energy. So that's why we're subtracting it. Okay. So we'll come down here. So I'm making an oxygen carbon bond here, another one here, and then a carbon-carbon single bond here. So I'm going to subtract. So I have 2 oxygen carbon bonds. So I'm going to come up here. Oxygen carbon bond is 358. So 2 times 358 kilojoules per mole plus a carbon-carbon single bond, which is 348 kilojoules per mole. Okay, so I'm going to subtract. So I'm going to go 2 times 2 times 358 plus 348. So I'm subtracting 1,064 kilojoules per mole. So the delta H for this reaction is going to be 760 minus 1,064. So it's going to be negative 304 kilojoules per mole, which means this is an exothermic reaction. So let's talk about that. Ultimately, that means that it's requiring more energy to create the bonds than it is to break the bonds. And that is why the reaction ends up being exothermic, because we're releasing more energy because it requires more energy to put those substances together. Okay, so that's the end of chapter 8. Thank you.